Let's take a moment and go through how to do the initial concentration of the solutions in the FeSCN equilibrium lab. The information that we're given is that we're using 5 milliliters of a 0.002 molar ferric nitrate solution, and we're going to dilute the 5 milliliters to a new volume of 10 milliliters. What we'd like to know is what's the concentration of the iron ions once we've diluted them to the volume of 10 milliliters. Now we're given the 0.002 molar stands for that we have 0.002 moles of iron ions per 1 liter. So this ratio is what we're given in the problem, that we have 0.002 moles of iron ions per 1 liter of solution. That comes from our symbol, the capital M here, which stands for molarity or moles per liter. We're only using a 5 milliliter sample, which is 0.005 liters of solution. So if we know that there's 0.002 moles in 1 liter, there's going to be X moles of Fe3 plus ions present in a sample that is 0.005 liters in size. Solving for X gives us that in this 5 milliliter sample, there's 1 times 10 to the negative 5th moles of Fe3 plus ions present. What we're going to do with the 5 milliliters of iron ions is we're going to take the 1 times 10 to the negative 5th moles of iron ions that are present in our 5 milliliter sample, and we're going to add enough water to this to bring the total volume from 5 milliliters now to 10 milliliters. And what we'd like to know is what is now the concentration of the iron ions in the 10 milliliter volume of solution that we've created. What we now know is that we have 1 times 10 to the negative 5th moles of iron ions, which we got from our 5 milliliter sample, but it's no longer in a 5 milliliter volume. We've diluted it so that the volume is now 0.010 liters. So we have 1 times 10 to the negative 5th moles of iron ions in 0.01 liters, which would be the same as X moles present in 1 liter. Once we have this in terms of how many moles are in 1 liter, that would be our concentration of the iron ions in the diluted solution. Solving for our new concentration gives us 0.001 molar Fe3 plus ions in the diluted solution. Now let's do an example with the thiocyanate ions. Here we're also given, we have 0.002 molar potassium thiocyanate. In this sample we're using 1 milliliter of that. We're going to dilute this to a volume of 10 milliliters. We'd like to know what's the concentration of the thiocyanate ions we're in the 10 milliliter now diluted solution. What we're given again is the capital M here gives us a known ratio. That tells us that we have 0.002 moles of SCN1 minus ions per 1 liter of solution. This is considered given information in the problem. However, the sample size we're using is not 1 liter, it's 1 milliliter, which is the same as 0.001 liters. So if we know that there's 0.002 moles of thiocyanate in 1 liter, there's going to be X moles of thiocyanate ions present in a sample that's 0.001 liters in volume. Solving for X gives us 2 times 10 to the minus 6 moles of thiocyanate ions are present in the 1 milliliter sample. The 1 milliliter sample of thiocyanate we're now going to dilute until it now has a volume not of 1 milliliter but of 10 milliliters. The 10 milliliter sample will contain the 2 times 10 to the negative 6 moles of thiocyanate ions that were present in the 1 milliliter sample. We'd now like to find what's the concentration of the thiocyanate in the now 10 milliliter volume of solution that contains the 2 times 10 to the negative 6 moles of thiocyanate ions. What we now know is that we have 2 times 10 to the negative 6 moles of thiocyanate and it's present in 10 milliliters, which is the same as 0.010 liters. If we know we have that many moles in 0.010 liters, we can solve for X moles that would be present when we have 1 liter of solution. Once we have this in terms of how many moles there are per 1 liter, that would be our molarity, or our concentration of the ions. Our concentration of this thiocyanate solution in the now 10 milliliter dilution comes out to be 0.0002 molar, and that would be the thiocyanate concentration in the now 10 milliliter diluted solution. The next part of the calculations involve using the Beer's law graph made in Tuesday's part of the lab, where we took known concentrations of FeSCN and measured the absorbance of them, and then made a plot of concentration versus absorbance. This gave us the slope of this line, and also, more importantly, the equation for the line, which we can now use to solve for any concentration of our FeSCN. If we can measure our X value, which is the absorbance, we can now calculate the Y, which would be our concentration of the FeSCN 2+ ions. The group data that we have here is this group did an absorbance reading of 0.610 for an unknown concentration of FeSCN 2+. What we can do is put the 0.610 in for our value of X, and then solve for Y, which will be our concentration of the FeSCN. Our X value here is the absorbance from our Beer's law plot that we made the previous day, using known concentrations of FeSCN. Solving for Y gives us a concentration of our FeSCN 2+ of 1.64 times 10 to the negative 4th molar. This is also the concentration of the FeSCN at equilibrium, in that the system, once we mix the chemicals together, it reached a state of equilibrium by the time we put the test tubes into the Spec 20. So this represents the equilibrium concentration of our FeSCN 2+ ions. Now that we have our equilibrium concentration of the FeSCN 2+, we can use the Rice strategy to calculate a value for our equilibrium constant, which is the goal in the lab exercise. At this point, here's what we know for our Rice strategy. Our initial concentration of the iron ions is 0.001 molar, and this is in the diluted solution of the entire mixture of the irons and thiocyanates. Our thiocyanate concentration is 0.0006 molar. Initially, the iron thiocyanate has a concentration of 0. We just determined that the equilibrium concentration using the Beer's law plot is 1.64 times 10 to the negative 4th molar for our equilibrium concentration of the FeSCN 2+ ions. This now allows us to figure out the size of our change, which we can then use to get our equilibrium concentrations. Our FeSCN has gone up by plus 1.64 times 10 to the negative 4th molar, and because the reaction is a 1 to 1 to 1 ratio in the balanced equation, that means each of our reactants had to go down by the same amount. So the reactants will be minus 1.64 times 10 to the negative 4th molar each. This will allow us to calculate the equilibrium concentration of each. We now know our equilibrium concentrations of iron ions, thiocyanate ions, and also the iron thiocyanate. The equilibrium concentrations now need to be inserted into the equilibrium constant expression, and we can calculate the equilibrium constant. This would be our setup for the equilibrium constant expression. It's a ratio of the concentration of our products divided by the concentrations of our reactants. Inserting the equilibrium concentrations into this expression will allow us to calculate the equilibrium constant. We've now inserted the equilibrium concentrations in for each of the products and reactants, and we can calculate our value for the equilibrium constant. This gives us an equilibrium constant value of about roughly 450 for our KEQ for the equilibrium of the iron thiocyanate equilibrium at room temperature.